Hi, so this is my attempt to answer question 31 from the homework. Okay, I'm going to go through parts A, B and C before I go on to D and E. So starting out, just a brief description of the problem. This is the situation here. This is a phototransistor. You can think of transistors as being like a gate that will allow current, electricity to pass in this direction. Okay, so from the positive voltage up here down to the negative voltage there. So they'll allow current to flow through that path, but they will only allow that under certain conditions. Okay, so most transistors will only allow that if you feed a small current into this point here, which is known as the base. Okay, into the base of the transistor. This is a phototransistor, which means that they'll only allow current to flow through here if there is some light shone onto the base. Okay, so what happens is the light shines onto the base of the transistor. That causes some electrons in the transistor to pass from being in the valence band, from the valence band into the conduction band. Okay, so suddenly we have conducting electrons in the semiconductor material in this transistor, and that means that current can flow through here. Okay, in the first part of the question, you're asked to determine the power, the amount of power falling onto this phototransistor. Okay, so if we think of this as being the surface of the phototransistor, we're told that that has an area of 2.25 times 10 to the minus 6 meters squared. Okay, that's the area of that transistor, and that so that's the area, and that the power density falling onto that, which is the amount of power per meter squared, is 4. So phi, which is usually the sort of symbol that we use for power density, phi equals 4 watts per meter squared. If we want to find the total power, okay, we use the formula P equals the area times the power density. P equals A phi equals 2.25 times 10 to the minus 6 times 4. And that works out to be 9 times 10 to the minus 6 watts. Okay, so that's the amount of power falling onto the transistor. For the next part of the question, they ask you to find the amount of energy in a single photon. Okay, a photon is a single little packet of light. Okay, light can be thought of as a wave or as a particle. If you think of light as a particle, an individual particle of light is known as a photon, and you can calculate the energy of an individual photon of light. Okay, and there's a formula that you use to do that. And if you look at the example on page 162 of the textbook, you can see that they've used the formula E P equals hc on lambda. Now, EP is the energy of the photon. H is this number known as Planck's constant. Okay, it's a very, very small number. We're going to use it a lot more in second semester. C is the speed of light, as we should all know, and lambda is the wavelength of the light. Okay, all of those things we're given numbers for in the question, so we can just substitute in the numbers. And we work out that E equals 6.63 times 10 to the minus 34, the value for H, times 3 times 10 to the 8, which is the value for C, the speed of light, divided by lambda, the wavelength, which is given in nanometers. Okay, so we have to recall what the prefix nano means. Nano means times 10 to the minus 9. So that is 536 nanometers, or times 10 to the minus 9 meters. Okay, and if we plug all of those numbers in to our scientific calculator, we get 3.71 times 10 to the minus 19 joules. Okay, so that's the number of joules of energy that are contained within a single photon, a single little packet of energy that make up the light falling onto the phototransistor. For part C of the question, we have to try and calculate the number of photons that are falling onto the phototransistor in a single second. Okay, so we have the energy of a single photon, and we have the power falling onto the power being absorbed by the transistor. Okay, now power is measured in joules per second. Okay, so that tells us how many joules of energy are falling onto the transistor in 1 second. So we know the energy of a single photon. We know the number of joules falling onto the transistor in 1 second. We can divide those two numbers together in order to find the number of photons. So we just get our solution from part A. Okay, 9.6 times 10 to the minus 9 times 10 to the minus 6 watts. Okay, which is the power, and 3.71 times 10 to the minus 19 joules, which is the amount of energy in a single photon, and we get N, the number of photons, equals power divided by EP. Okay, the power falling on divided by the energy of a single photon equals 9 times 10 to the minus 6 divided by 3.71 times 10 to the minus 19. Again, plug it into your scientific calculator and you find the solution that N equals 2.43 times 10 to the 13 photons per second. Okay? On to part D. For part D, we now have to find the current flowing into the base. Okay, so the what's called the photocurrent, which is the amount of electrons freed by this light falling onto the base here, creating a very small current. Okay, now we know the number of photons that are falling onto the base. We just calculated that in the last part of the question. Right, and the question asks us to assume that every single one of these photons, okay, causes an individual electron to jump into the conduction band and become a conducting electron. So that's what we consider to be the base current, all those electrons flowing into the conduction band, or moving into the conduction band, starting to flow there. Now, to answer this question, we have to think about what does current actually mean. So current, I, is actually a measure of the rate of flow of electricity, okay, and of electrical charge. Electrical charge is measured in coulombs, and rates of most things are measured per second. Okay, so current is actually a measure of the number of coulombs per second. Now, if we know the number of photons, we're going to say that that's equal to the number of electrons per second. Okay, that's what the question asks us to assume. So that's the number of electrons per second as well. All we need to know then is how much charge does each one of these electrons correspond to. And we're told in the question that the charge on an individual electron is E equals 1.6 times 10 to the minus 19. Okay, so to calculate the current, we use I equals the number of electrons per second multiplied by the charge on an individual electron equals 2.43 times 10 to the minus 13 times 1.6 times 10 to the minus 19. Okay, and if we calculate that, we get equals 3.88 times 10 to the minus 6 amps. Right. On to the final part of the question. In the final part of the question, it wants us to find the current gain of the transistor. Now we know that gain from our study of amplifiers is the current gain, for example, is equal to the output current divided by the input current. Okay. In this case, actually, we're going to be doing this current here. Okay. So I'll still call that the output current divided by the photocurrent. Okay. The photocurrent being the current that we're inducing in the base here. So I'll call that IP. IP we've already calculated, so we just need to calculate the output current, which is the current flowing through here. Now, to do this, we can go back to some of the knowledge that we've gained from studying voltage dividers, okay? And we know that the output voltage here is, in this case, 10 volts, which means that if that's 14 volts there, then the voltage drop across that 20 kilo ohm resistor must be 4 volts. Okay, to make up that total of 14. So if we know the voltage across the transistor, across the resistor, and we know the value of the resistor, we can use Ohm's law. I equals V over R. So that output voltage, output current there is the voltage there divided by the value of that resistance. So that equals 4 over 20,000 or 20 kilo ohms. And if we calculate that, we find that that is equal to 0.2 milliamps. Okay? So, plugging then the output current along with the photocurrent that we calculated in part D into this equation, we get I equals 0.2 times 10 to the minus 3, okay, 0.2 milliamps, divided by 3.88 times 10 to the minus 6, and that equals 51, okay, which is the value of the gain. So the output current here flowing through the transistor is 51 times the photocurrent induced in the base. Hopefully that answers the question clearly enough. Sorry if I've gone on. Have a good holiday.